Okay, so in the last video, we saw how we can develop a rate law for a catalytic reaction based on a mechanism that we hypothesized for that reaction. So we had looked at the NO oxidation reaction, and this is the mechanism that we derived. And in that exercise, what the method by which we got the rate law was to assume a rate determining step. So in that case, we had assumed that step 3 was rate limiting. We said that the entire reaction, the rate of the entire reaction would be equal to the rate of the rate limiting step. So all the other steps we assumed would be fast, and this step we said is going to be the bottleneck step. So the rate that we observe will be basically the rate of this reaction. That all of the other reactions in this mechanism, all of the other steps are going to be relatively fast. So we made the assumption that they are all in equilibrium. And we used all of that information to write expressions for the various terms in the rate law for step 3, which we set equal to our rate. And the goal of that was to reduce the rate law down to a rate constant times a function of concentration, which we did. We also said we didn't exactly meet the experimental observation, but that's because that was an actual research case, and that if we would have spent more time developing the mechanism, we could have come up with a reaction mechanism. But doing that is beyond the scope of this class, given that we don't have a bunch of time to spend researching mechanisms of reactions. We just want to kind of give a feel for how that would work. So in this lecture, we're going to use a different model to obtain the rate of reaction. The model that we're going to use is called the pseudo-steady state hypothesis, or PSSH. So in the pseudo-steady state hypothesis, we don't make any assumptions about which step or steps are rate limiting. Instead, we make the assumption that the net rates of all the catalytic intermediates are equal to 0. So by catalytic intermediates, I mean all of the species in the mechanism that aren't reactants or products in the overall reaction. So the overall reaction here is 2NO gas plus O2 gas goes to 2NO2 gas. Hence, NO, O2, and NO2 gas are not reaction intermediates. All of the other species in the mechanism are. So NO star, O2 star, O star, NO2 star, and star itself, those are all catalytic intermediates. So under the pseudo-steady state hypothesis, we say that the coverages of all of those species are going to be, or the rates of formation of the coverages of all of those species are going to be equal to 0. So let's see how we could apply the pseudo-steady state hypothesis in this example. So what we want to do is say that the net rate of all of our catalytic intermediates is equal to 0. So let's write those all out. So for NO star, I have NO participating in reaction 1 and also in reaction 4. So that would tell me that R1 net minus R4 net is equal to 0. So NO is being formed over here, so the net rate of generation in reaction 1 is positive. NO is being consumed in reaction 4, so the net rate of generation is negative. So when I put those together, I get R1 net minus R4 net is equal to 0. And similarly, I can do this for all of my reaction intermediates. So R net O2 equals 0, and that's going to equal R2 net minus R3 net. NO2 is going to be R4 net minus R5 net. And O is going to be equal to 2 times R3 net minus R4 net. And then we could do the same thing for the free sites. This is actually a restatement of everything that we've just written because the sites balance. So if all of the net rates of formation of everything else is equal to 0, then that means that the net rate of formation of free sites is also equal to 0. So I can write this expression out, but I'm not going to use it when I go to make a solution. So usually when I write the pseudo-steady state hypothesis, since I'm not making any assumptions about which steps are rate limiting, I would treat all of the reactions in the mechanism as potentially reversible. So they're all going to have forward and reverse rates. And again, I would treat them all as elementary. So I could go through and fill out all of these expressions based on the elementary rate laws that I would come up with. And then beyond that, there's basically 2 ways to solve this system of equations. In the first way, so the unknowns here would be the different coverages of the different species. So I'm not going to fill in the expressions for the different coverages. So in the last example, the rate limiting step example, we made the assumption that certain reactions were in equilibrium. We said if they are in equilibrium, then we can relate the coverages of the different species to the gas phase concentrations and the equilibrium constant of those reactions. We're not doing that in this example, so we don't have a way to write an expression for the different coverages. So those all remain to be theta star. So for example, so we'll say in this case, we'll say this methodology, we'll say we are not making assumptions about which steps are fast or slow. So in other words, we can't assume that, for example, step 1 is fast, or relatively fast, and hence an equilibrium. We can't make that assumption. So because of that, we end up not having expressions for the coverages of our different species. So let's show an example. We said that the net rate of NO is equal to R1 net minus R4 net. So what that means is I'm going to have 0 is going to be equal to K1 forward CNO theta star minus K1 reverse theta NO minus K4 forward theta NO theta O plus K4 reverse theta NO2. And let me actually write this down here. And let me make sure I got that correct. Yes. So we would end up with a system of equations. So unknowns that we have are theta star, theta NO, theta O, theta NO2. If we were to write out the full system of equations, we'd also have theta O2. So we have 5 unknowns. We would need 5 equations. So here are 4 of our equations, and the 5th equation is the site balance, which is theta star equals 1 minus the sum of the other coverages. So we can solve that, and in fact, when we do kinetic modeling, that's exactly what we do. So we would solve for the different coverages. The coverages would then allow us to also get a steady state rate. So the way we get the steady state rates, when we make the solution for the coverages, we're going to be able to calculate the forward and reverse rates for all of these reactions. Some of those solutions, the forward and reverse rates are going to be almost equal to each other, so we'll end up finding that those reactions indeed are in quasi-equilibrium. So we end up solving for that rather than having to make the assumption. Some of these reactions will be the forward rate will be appreciable and the reverse rate will not. What that means is that those reactions are irreversible. Those are most likely the steps that are limiting the rate. In that case, there can be multiple rate determining steps. So for example, in this example, we might find that both of these are contributing to the observed rate. In that case, the only difference between their forward rates would be based on the way they play into the overall gas phase reaction from a stoichiometric standpoint. So the rate of reaction 4, for example, this reaction would have to turn over twice in the time that this reaction turned over once. So the rate of reaction 4 would be equal to 2 times the rate of reaction 3. That expression, either the rate of reaction 3 or 2 times the rate of reaction 4, would be the rate of the reaction. So the pseudo-steady state hypothesis we often use in kinetic modeling. When we do this sort of solution, we usually use a computer to solve the system of equations because, as you can see, it gets kind of messy. Alternatively, we can make assumptions about a most abundant surface intermediate. This, of course, once we start making assumptions, we tend to decrease the robustness of the model because for the model to work, it means the assumptions have to be true. So the fewer assumptions you have to make, the better. But we can make an assumption. We can make assumptions about the relative coverages. So, for example, we may assume theta O is close to 1 and theta everything else is close to 0. If we were to do that, then the only expression that we would need to solve would be this expression. All of the other expressions would go to 0 because their rates would be so small. In that case, we would be able to, it would be easier to solve for the coverage of it would be easier to solve for the coverages of the different species. What we would do then is put that, or to use that information to solve for the coverages of oxygen, atomic oxygen, and nitric oxide. If we do that, what we want to find is that the coverage of oxygen indeed is close to 1, and the coverage of nitric oxide and free sites are close to 0. If we don't find that, then the assumption that we made is not correct. So that is the pseudo-steady state hypothesis, which is another method that we can use to learn about the rates that come from reaction mechanisms.